In December 2024, OpenAI unveiled GPT-5 with groundbreaking multimodal reasoning capabilities that stunned the AI research community. These large language models have evolved beyond text generation. They now engage in complex problem-solving, scientific discovery, and even creative collaboration that rivals human experts. But what truly happens inside these neural architectures when they think? How do billions of mathematical operations transform into coherent reasoning? Today, we'll dissect the cutting-edge mechanisms behind modern LLMs, from transformer innovations to test time, compute scaling, and explore what lies beyond on the frontier of artificial general intelligence. Before an LLM can process language, it must first compress human text into dense mathematical representations. Modern tokenizers like GPT-5's BPE variant can encode over 200,000 unique tokens, capturing not just English words, but code syntax, mathematical notation, and 100 languages with subword granularity. Each token is then mapped to a point in a high-dimensional embedding space. For GPT-5, that's 288 dimensions. These aren't arbitrary coordinates. Through training on trillions of tokens, the model learns to position semantically similar words closer together in this geometric space, creating what researchers call a semantic manifold. The geometry of this space encodes analogies: king minus man plus woman approximately equals queen. This is vector arithmetic performing linguistic reasoning. The transformer architecture, introduced in the landmark 2017 paper Attention Is All You Need, fundamentally changed how machines process sequential data. Unlike recurrent networks that process tokens one at a time, transformers leverage massive parallelization through their self-attention mechanism. In GPT-5, each of the 120 transformer layers contains up to 128 attention heads, that's 360 parallel attention computations happening simultaneously. But here's the key innovation: self-attention allows every token to directly attend to every other token in the sequence. There's no distance penalty. The model can connect ideas separated by thousands of words instantly. Modern architectures have evolved further. We now have mixture of experts layers, where only a subset of the network activates for each token, dramatically improving efficiency. GPT-5 reportedly uses 16 expert subnetworks, activating only 2 per token. And with innovations like rotary position embeddings and grouped query attention, these models can now handle context windows exceeding 1 million tokens, that's roughly 750,000 words, or 10 full novels processed simultaneously. The most significant breakthrough of 2024 wasn't just making models bigger, it was making them think longer. OpenAI SO series models introduced test time, compute scaling, the ability to spend more computational resources during inference to solve harder problems. Traditional LLMs generate answers in a single forward pass. But O1 and O3 models can think for minutes, internally generating chains of reasoning that can span thousands of tokens before producing the final answer. This mirrors human deliberative thinking. When you solve a complex integral, you don't blurt out the answer, you work through steps, check your work, maybe backtrack if you make an error. O3, released in early 2025, achieved a remarkable milestone. It scored in the 96th percentile on the International Mathematical Olympiad, competition where human gold medalists typically score in the 99th percentile. The key is structured reasoning. These models generate internal monologues, evaluate their own confidence, and even debate between multiple reasoning paths before committing to an answer. Training a frontier model like GPT-5 is an engineering marvel that pushes the boundaries of what's computationally possible. The training dataset spans 15 trillion tokens, equivalent to every book ever written, multiplied by 10,000. It includes web pages, scientific papers, code repositories, and multilingual text spanning over 100 languages. But raw scale isn't enough. Modern training employs sophisticated curriculum learning. The model first learns basic patterns, then gradually encounters more complex reasoning tasks. The computational requirements are staggering. GPT-5 self-training run utilized an estimated 25,000 NVIDIA H100 GPUs running continuously for 4 months, consuming roughly 50 megawatt-hours of electricity, equivalent to powering 4,000 homes for a year. And the process isn't simply minimizing prediction error. Engineers use techniques like learning rate schedules, gradient clipping, and careful batch size scaling to navigate the treacherous landscape of optimization. One wrong hyperparameter choice could mean the difference between breakthrough performance and catastrophic failure at a cost of millions of dollars per experiment. A pre-trained language model is like a brilliant but amoral savant. It knows everything but has no judgment about what it should say. This is where reinforcement learning from human feedback, or RLHF, becomes essential. The process begins with human labelers rating thousands of model outputs: helpful versus harmful, truthful versus deceptive, harmless versus dangerous. These preference labels train a reward model, a separate neural network that learns to predict what humans would prefer. This reward model then guides the language model's fine-tuning through proximal policy optimization. Anthropic, the company behind Claude, pioneered an additional technique called constitutional AI. Instead of relying solely on human feedback, they define a constitution, a set of principles like be helpful but not manipulative or refuse illegal requests politely. The model critiques its own outputs against these principles, revises them, and learns from self-generated improvements. It's a form of AI teaching itself to be more aligned. The result? Modern chatbots that refuse to help with harmful requests, admit uncertainty, and maintain consistent values across conversations. But the question remains, whose values are we encoding? Every conversation with an AI happens within what's called a context window, the model's working memory. Early models like GPT-2 could only remember about 1,000 tokens, roughly 3 paragraphs. Ask a question referencing something from earlier? The model had already forgotten. This changed dramatically with GPT-4's 32,000 token window, then Claude 3's revolutionary 200,000 tokens. You could feed it entire codebases or legal documents. But 2025 brought the next leap. Google's Gemini 2.0 supports 2 million tokens, and experimental models from OpenAI are testing effectively unlimited context through memory augmentation. The technical challenge is computational. Self-attention scales quadratically with sequence length. Double your context window, and computation increases fourfold. Researchers have developed ingenious solutions: sparse attention patterns that skip irrelevant tokens, memory-efficient attention algorithms like Flash Attention 3, and external memory systems that store long-term information outside the model's immediate context. The ultimate goal? An AI that maintains perfect memory across months of conversation, learning and adapting to each individual user, a persistent digital collaborator that never forgets. The next evolution of LLMs isn't just better conversation, it's autonomous action. In 2024, we saw the emergence of AI agents, systems that can plan multi-step tasks, use tools dynamically, and operate with minimal human supervision. OpenAI's ChatGPT can now browse the web, execute Python code, analyze images, and generate charts all within a single conversation. Anthropic's Claude can interact with computer interfaces directly, moving cursors and clicking buttons like a human user. But the real breakthrough is agentic reasoning, the ability to decompose complex goals into subtasks, execute them sequentially, handle failures gracefully, and adapt plans based on feedback. Consider this scenario. Launch a marketing website for my bakery. A 2023 chatbot would give you advice. A 2025 agent actually builds it, researching competitors, generating design mockups, writing HTML CSS code, creating logo variations with DALL-E, testing responsiveness across devices, and deploying to a hosting service. Companies like Cognition AI have demonstrated agents that can contribute to large codebases, debugging thousands of lines of code and submitting pull requests autonomously. The philosophical shift is profound. AI is moving from a passive tool you query to an active collaborator that pursues goals independently. We stand at an inflection point in technological history. Current large language models GPT-5, Claude Opus 4, Gemini 2.0 are extraordinary narrow AI systems. They excel at language tasks but lack the generalizable intelligence that humans possess. The next milestone is AGI, Artificial General Intelligence, a system that can learn any cognitive task a human can, transfer knowledge between domains seamlessly, and reason about novel situations without task-specific training. Leading AI labs have diverged on timelines. OpenAI CEO Sam Altman suggested AGI could arrive by 2027. Anthropic's Dario Amodei estimates 2026 to 2028. DeepMind's Demis Hassabis predicts the next decade. Skeptics like Yann LeCun argue we're missing fundamental insights and AGI remains decades away, but one thing is clear: the pace of progress is exponential. GPT-2 to GPT-3 was an 100 scale increase in 18 months. GPT-3 to GPT-4 brought emergent reasoning in 2 years. If this trajectory continues, and that's significant if the capabilities gap between current AI and human-level intelligence may close faster than most expect. Beyond AGI lies an even more profound question: artificial superintelligence, or ASI, systems that surpass human cognitive ability in every domain. At that point, we enter territory without historical precedent. The choices we make now in AI safety, alignment, governance will determine whether this technology becomes humanity's greatest tool or most existential risk. In just 3 years, large language models have transformed from research curiosities to foundational technologies reshaping society. We've journeyed from tokenization to transformers, from training at scale to test-time reasoning, from chatbots to autonomous agents. These systems don't think like humans. They predict, pattern match, and optimize through billions of mathematical operations. Yet somewhere in that complexity, something resembling understanding emerges. The models we build today are just the beginning. As we scale compute, refine architectures, and solve alignment challenges, we inch closer to artificial general intelligence machines that don't just process language, but truly reason about the world. This channel will continue exploring the frontier, diving into cutting-edge papers, explaining breakthrough techniques, and examining the philosophical questions at the heart of AI. Because understanding how AI works isn't just technical curiosity, it's essential literacy for navigating the future we're building together. Subscribe to join the journey into the age of thinking machines.